Okay, welcome back. I'm looking at the 2016 DEB paper 2, and I've just got started on the easiest question, which is to find if a equilateral triangle has an area of 9√3, find its side length. So we set the area to using the formula half AB sine of theta or sine of c. Okay, you find that formula here on page 16. Always keep reminding yourselves every time you use a formula what page it was on. So page 16, and just want to roughly construct that. I'm just going to break this into 3:2 because I know that that's where the center is. So just around here, we just eyeball it. I don't mind if I'm a little bit out. I just want to model this construction. Okay, so basically, what's exceptional about a equilateral triangle is that the medians, the angular bisectors, and the perpendicular bisectors are all concurrent. They all meet in one point. Okay, and for that reason we know that this is a right angle. Why do we know that? Because it's a perpendicular bisector, and we know that the angular bisector splits the 60 into 30 and 30, and we know that this full length here was 6, and obviously the perpendicular bisector has split that into 3 and 3. Okay, so at that stage we can dispense with, we can extract the right angle, the 30, 60, 90 from that triangle with the knowledge that this is 3, this is 30 degrees, and go from there. Now while we don't need it, well yeah, we can go straight in to say that this, the shorter length takes the middle length and divides it by √3, because to go from there to there is multiplied by √3. Well, the inverse of that is to divide by √3, and that's equal to √3. Because, okay, that's equal to √3. So find in terms of pi. So basically we have now, we can go back now and say, sure, our circle has a radius of √3. And now the area of a circle is equal to pi r squared, which is equal to now pi times √3 squared, which is equal to 3 pi. Okay, check for units, 3 pi centimeters. That's the exact answer. That's the way we should be giving it. Well, we have given it. Find the area in terms of pi. Fine. Okay, moving on now to part B. Okay, what do we got here? I'll give you a chance to read it. And you should be working off your, this should be supporting your work on your own exam paper that you've hopefully printed. If you're working from a computer screen, try to just draw it out. It's good practice anyway to write out the questions, so don't consider that a major disadvantage. Use it to your advantage. Okay, so we have a radius of 90 centimeters. And we know that OM is 30 centimeters. Okay, so let's be careful. You can start jumping to all sorts of conclusions and putting down data, but we need to just think about data we need. So I'm going to refrain from putting down how deep it is. So the only thing that I need to know write right now, is that we already have 2 dimensions of a right angle triangle. I'll keep returning to my set square here. So basically, if I could extract that, what I'm saying is this is sitting in here with, sorry, it's not exactly 30 degrees, but this is sitting in here but it is a generic acute triangle, so we'll just use it to help us modeling. So that's there like that, and what we would like to do, we know that if we're find AB, so we just need this length, and it looks to me like Pythagoras is the best way to go. So let's just go 90 squared plus 30 squared in our calculator. Okay, we get 30 root 10, and I'm going to store that to the first memory bank. 30 root 10. No, yeah. If you're going to, I really highly recommend you get the FX, because the others are going to become more and more difficult to get, and this is a way better calculator, so I'm not going to work on that at all. Because you could see there I got caught with a keystroke sequence which was slightly different between them. So I'll go again here and say, and it was just to do with dropping the memories in. So this is the FX, the newer FX, and they'll be widely available and cheaper than the other one at this stage, and a far faster, higher resolution calculator. The text isn't huge in them, but there are ways of making it bigger. Okay, so we do get 30 root 10 for x, but remember they want double that, so 60 root 10. That should have been minus. Okay, I'm going to leave this in because apologies for that. Okay, so that should have been, and of course it should have been minus. So and I want to put this in for one reason. I'm showing you, you're literally seeing the process of learning. Learning does not, it generally happens when somebody is figuring things out for themselves, not when you're reading a chapter in a book in a sequential manner and you don't know why you're learning it. So now that is such an elementary error I made, whereby the application of Pythagoras, where the hypotenuse c squared is equal to a squared plus b squared as written in your tables. You're just about to be that's lethal if you mix up the hypotenuse with the legs of the triangle, which I did by dropping the ball and just not concentrating. And that had to turn into a minus, and I got 60 root 2 in my calculation. I also have to remember that really I should be writing up here and realizing that this is just a step along the way and I need 2 in front of it. So I end up getting that AB is equal to 120 root 2, and that's insert form, so that's perfect. Now we're to find the angle at O. Okay, so we have this length here in centimeters and we have this length. So my suggestion is we can go via the cosine rule, because we also have 90 here. But it's quite tedious, and we're better off to use the fact that there's symmetry here to return to 60 root 2 90, and it looks like sine, and we're going to double the angle, so we'll double it up front and say double the angle whose sine is 60 root 2 over 90. Okay, I'll take out those two notes now. 6 root 2 over 9. So you put that into your calculator as double the angle whose sine, double check, are we good for being the angle whose sine? Yeah, once you're looking at opposite. So the angle whose sine is 6 root 2 over 9, fraction bar, 6 root 2 over 9. Okay, now we get 141. By the way, just another point back there. I had made a mistake and I felt there was something wrong, but what I didn't show you is that one of the reasons for a digital expansion. If I had done a digital expansion on the answer that I got when I had used plus, then this length would have turned out to be bigger than that length, and that would have been an immediate red flag. So, and that's one reason why when we're expressing exact forms with pi and root 2, it's always, and that is a nice way to write them exactly, but we should always just kind of look at them in their digital expanded form without any fundamental, the constants like pi and so on. Okay, just in order to check common sense, make sure they pass common sense tests. So I'm getting an angle of 141.06, and I'm just going to trust that that's correct. Okay, so the angle up here is 141.06 opening out towards that sector. Hence find the area of the shaded region. Okay, so the way we're going to find this shaded region is we're going to take a sector area, which is the entire sector out to the edges, minus the triangle area, minus the area of the triangle. Okay, now the sector area is half r squared theta, provided theta is in radians. Very easily converted into radians by using the conversion factor. Okay, now the way to remember which was which is to put the degree symbol here, and remember the degree symbols must cancel, so it's 180 degrees at the bottom to cancel and pi at the top. Now you could also do this using the degrees formula, and it essentially amounts to the same thing. Where do I need to go now? Think back here. Okay, page 9. So I could also just take the sector area. Look at this, arc is on the left, sectors is on the right, radians is on the top, degrees is on the bottom. So I could use pi r squared theta over 360. I think we'll go with that then. Okay, so because I'm kind of going, so we'll scratch that, and we'll go pi r squared 141. Now 141.06, or this number I have here, is quite a mess, so I'll store it to a, and that's what this calculator becomes really quick for doing those sort of things and speeding up your dealing with messy numbers. Even if you have to write 4 or 5 digits, it still drains the time. So so what I'll do is I will just store it to a, and I will remind myself, I will note that fact here, that this has been stored to a. Just like the calculator just goes, that has now been stored to a, or there's an arrow to a. I do exactly what the calculator says. So I'm doing exactly what the log tables say for the area of the sector, and I've decided not to bother switching to radians. So we're getting, let me scratch that here. Let me write the formula first. So it's pi r squared. Now a, because I'm using the angle a, over 360 degrees. And then we're going to want to get the area of the triangle, which is down here. Now, what's interesting is there's no a here, because that's just the way there's no half here, and that's fine. So that's written there, that formula, and then we're going in to the formula, to this formula here, which is minus half r squared, the sine of the angle between them, which is the sine of A. Okay. Now r is excuse me, r is 90. But I don't need to spend forever here. So here goes. We'll get the calculator out and get started. So shift pi multiplied by 90 squared. Now I can recall A without the multiplication symbol, and I can divide by 360. That's that done. Okay, moving forward. Minus. Whenever there's any sort of fraction at all, start your fraction bar. And I've got 90 squared multiplied by, and this is where things become really handy, just the sine of A as I recall it, like that. And down we go. And down we go to just a simple 2. Okay. And we get 7425 centimeters cubed. Centimeters squared. Okay, moving on to the next part of the question.